Hello, my dear. I welcome you all in this session of challenging question. So, my dear, what is the motive of this series? The motive of this series is only is that to understand, that means you have to know the types, which types of questions you supposed to be asked in the upcoming gate. Like that means we have an exam, a mechanical exam at 3rd of February and civil at 4th of February. So just don't, if you are not able to solve, thank you. If you are not able to solve, don't bother about that questions. Okay, just go, just compare your level. That means compare your practice level, compare your concept level according to that the given problem which I will discuss today. Okay, so in this session we will cover good question. We'll take the good questions, and along with that we have to complete solution for that one also. So be patient and stay tuned with me. Okay, so we start the first question from the basics one. That means we intuitionally we start the question from dynamics, boundary layer, drag analysis, compressible fluid flow, like that. And really this question is very helpful to enhance your concept. So don't bother about that case, sir, that problem is very tough or easy. Don't bother about that. Don't judge your level with respect to this concept, but you just to try to understand that type of question whether you have to already done or not. Okay, so let's start with this one. The first question is this one. Please see the first question. The first question, read that question, beta. What they says that the first question is says that water flow through a circular nozzle exits into the air as a jet and strike a plate. The force required to hold the plate steady is 70 Newton. Assume frictionless one-dimensional flow. Estimate the mercury manometric reading. That means you have to find this H value. You have to find this H value. Okay, so what is this H value? Okay, so what the question is says that, see my dear, this is the nozzle, and in the nozzle the area it is given, that means diameter it is given, that means you have to area, that means the area of the cross section it is given here, and area of the cross section d2 it is given here. Now it will in swing the jet into the air, that means the exit, that means if you take this section, if you take this section is your 1 and this section is your 2. Okay, and you have to find the H level. How to find this mercury level? Please find it. And while striking, after the striking of the fluid on the plate, this says that assume the frictionless and one-dimensional also. That means there is when the fluid will strike on the plate, the fluid will glide over the plate. So during the gliding, there is no any resistance. Okay, so you cannot bother about the resistance. What is the resistance? Okay, my dear. How to start this problem? And in this one, it is given density of the water. It is given. You have to take density of water is equal to 998 kg per meter cube, and density of mercury it is your 1356. It value it is given 7. So you are taking this value 78 kg per meter. So mercury and water density it is given. Now you have to find this manometric deflection. Okay, this manometric deflection. So what is your approach? Please think. What is your approach? Please think. What is your, how to start this problem? That is the main things. How to start this problem? That is the main things. How to find this manometric deflection? See, my dear, think that if the plate is not given, it is like that, the question it is asking like that, the water is flowing through the nozzle, converging nozzle, and you have to install a manometer, find H deflection. So please tell me, at a given data, you have to able to find H value, yes or not? See, forget about this this portion. Forget about this portion. Only there is a nozzle. The deflection, manometric deflection, it is there. It is ensuing at a diameter D2, entering at a diameter D1. Find the H. You have to able to find this H value. Yes or not? See, that such type of analysis you must have to knowledge about that. Okay, sir. If so, what data you have to required when there is no any plate is there? What data is required? So that means in that case the data is insufficient. You cannot find. Why? Because at least one section you have to knowledge about that. See, if you apply the continuity equation between this section A1, V1, A2, V2, you have, but V1 and V2 don't have. V1 and V2 don't have. Also, if you apply the energy equation, why? Because there is a frictionless energy equation, that means a Bernoulli equation, total energy at this section A and total energy at this section 2. So, but you don't have the pressure at A and pressure at B. So, the pressure is also don't know, velocity also we have don't know. So, how to find this H value? So, for that one, what you have to do? You have to place a plate here. This is the interview question. How to find why this value it is given? The motive of this value is you have to find the exit velocity, impact velocity. If the fluid is flowing through the nozzle and if you place the hand in front of that jet, so what you have the impact, you know this one. Due to this impact, you have to find the exit velocity. Once you have to find the exit velocity, inlet velocity you have. Once you have to find the inlet and exit velocity, you also find the pressure difference. Once you have to find the pressure difference, you can easily find the H value. This is your format, okay? So, let's start with this one. Okay, beta? So, this is your H. Okay. Now, let's suppose this is our section 1. This is our section 1. This is our section 2. Okay. Section 2. Okay. Now, we apply first the momentum equation. We apply the first momentum equation. What is the momentum equation? Summation of all the force. We know that. For this control volume. This is our control volume. Okay. This is our control volume. This is our control volume, okay? This is our control volume, okay? This is our control volume, okay? So, summation of all the force is equal to F, that force in x direction, and that force it is your negative. That means if you put this x direction x and this is your y, this is your y. So, F is equal to minus, in a y direction we are not bothered about that. Why? Because we have to find the force in x direction. So, x direction inlet it is there, but in the x direction exit is not there. Why? Because there is a plate. Exit it is in y direction. So, if you apply the force equation in x direction, there is no any exit condition. So, F summation of all the force is equal to F, and that F is a minus. What is that? Mass flow rate in minus U at in. What is the mass flow rate? Mass flow rate, that means mass per unit time. So, mass per unit time into velocity. Mass, velocity by time, acceleration. So, this is nothing, this is a force, mass into acceleration. Why move negative? Why? Because this force is negative direction. Clear? Now, what is mass flow rate? What is the mass flow rate? What is the mass flow rate? We know that. Density by mass by volume. So, mass flow rate rho m dot area into velocity. So, from here you can easily write down like that. This F is equal to minus of m dot is what? Rho a u I square. Clear? Clear? This is the impact. This is your impact. Now, Now my dear, the force it is given. In this one, the force it is given. How much? See my dear. The force required to hold the plate steadily at 70 Newton. So the force it is given 70 Newton is equal to minus density. This is the density of water. Why? Because this is the water. This is the water. Okay, this is the water. So density it is given 998. Area. This is your what? In. Yes or not? This is your in. So in it is in here. This is your in x direction, not this in. Understood? This is not at in. This is your in into the control volume. So this is your control volume analysis. So in it is in control volume. This is our control volume. So put the area of this one, this jet, not this one, beta. Okay? So there may be a little bit confusion. So just this in into the control volume, and this is your control volume. So in it is there. In it what area? This 3 centimeter. That means pi by 4 0.03 whole square diameter. And what is the velocity? You don't have a velocity. So in it is your V2. In it is, what is the in velocity? In velocity is your V2. Okay. So from here you can easily find what is the velocity V2. So V2 it is there 9.96 meter per second. Here you can you may ask me, sir, why the negative? How to justify the negative? See, this m it is in, and this force it is in negative direction. So here this is minus 70. Okay, this is negative direction. Okay, so this is this velocity. At this velocity, the fluid will be impact on the plate due to this velocity. So this is the velocity impact velocity. Impact velocity. At this velocity, the jet will strike on the plate. Clear? Now, the second task is that how to find this inlet velocity. Apply the continuity equation. What is that? A1 V1 continuity equation. So this is your dynamics momentum equation. This is your momentum equation. Now continuity equation. What is the continuity equation? A1 V1 is equal to A2 V2. Put all this value. A1 you have. So from here you can easily find V2. What is V2? V2 you have to find V1. Sorry. From here you can easily find V1 value. V1. So what is V1? V2 A2 upon A1. Yes or not? What is V2? V2 you have 9.96. What is A2? Pi by 4. Area it is your 0.1 square. Yes or not? So this is your V2. Yes. So A2. A2 is this one. No? This is A2. So A2 is 0.3. 0.03 whole square. This is your A2 divided by A1 pi by 4 0.1 square. If you solve this one, from here you can easily find V1, and V1 is 0.9 meter per second. This is your velocity at inlet. This is the velocity at inlet, and this is the velocity at exit. So my dear, if there is a plate is there, what is the impact velocity you have? Once you have to find the impact velocity, you can easily apply the continuity equation and find the inlet velocity. That means velocity at the pipe. This is the velocity in the pipe, and this is the velocity of a jet. So indirectly this is the velocity of jet. And this is the velocity of flow velocity, velocity in pipe. Velocity in pipe. Clear? Now, once you have the velocity in pipe and velocity of jet, you can easily find the pressure difference by applying the Bernoulli's equation. Okay? So, So once you have okay, so using Bernoulli's equation, what is that? You know this? P1 minus P2 is equal to half rho, this is for water, V2 square minus, yes, why? Because there is a horizontal, there is no any pressure. So this is your Bernoulli's equation, P2 minus P1 half rho. You have a V2, you have V1, you have a density. So from here you can easily find P1 minus P2. Put all this value, no problem. Density of water, it is given how much? 998. Velocity, how much it is given? V2. V2 is how much, beta? V2, it is your 9.96. 9.96 whole square. V1 is how much? V1, it is your 0.9. 0.9 square. So from here you can easily find pressure difference, that is your 49,100 Pascal. This is your pressure difference. Once you have a pressure difference, you can easily find the manometric deflection. What is the manometric deflection, beta? H. See the beauty, very important. Delta P by delta rho into G. This is your manometric deflection. This is the formula. You know that, pressure. Why delta rho? Why? Because the density is different. So delta P is equal to rho GH. You know that P equal to rho GH. So H is equal to delta P by delta rho into G. Now what is delta P? This is your delta P. Delta P, it is your 49100 divided by delta rho. Delta rho, it is what? Density of what? Whose density is higher? So density is higher for this one, mercury. So mercury, that means rho G minus rho W. Rho G minus rho W. So from here, rho G, it is your 13,567.78 minus rho W 998 into 9.81 into 9.81. Calculate this value. From here you can easily find approximately 0.4 meter. This is clear, beta, everyone? So my dear, in this question there are three formulas applied. First one, the Bernoulli's equation. Second one, the continuity equation. Third one, the dynamic equation, matlab momentum equation. So from the this is your what? Conservation of momentum, conservation of mass, and conservation of energy. So from these three equations we can easily find. So in this question, all the three conservation you have to apply, must be applied while calculating this problem, while solving this problem. This is your energy equation, this is your conservation of mass equation, and that is your conservation of momentum equation. So from the conservation of momentum equation, you can easily find the exit velocity, jet velocity. With the help of conservation of momentum equation, apply the conservation of mass equation, you can find the inlet velocity in the pipe. After calculating the kinetic, that means velocity difference, apply the Bernoulli's equation, find the pressure difference. While you applying the pressure difference, Bernoulli's equation, you can easily find the pressure difference. Once you have to find the pressure difference, you can apply the manometric equation and find the manometric deflection. Clear? Clear? This is clear, beta, everyone, please. This is clear? Now, once this is clear, go to the next problem. This is your next problem. Please see this one. Now, in this one, this is not a manometer. Please mind it. This is not your manometer, beta. This is not your manometer. This is your U-tube. This is your not U-tube manometer. This is your Pitot tube. See, this is your Pitot tube. Okay. So just see this one. What is this question? I will read the question. What is that? In figure, the flowing fluid is carbon dioxide. Carbon dioxide act as an ideal gas. You can take like that. Flowing fluid is carbon dioxide at 20 degrees centigrade. Neglect the laws. If P1 is pressure at the section 170 kilopascal, and the manometric fluid in marine red oil, that means this is your manometric fluid, it is given, specific gravity it is given 0.827, estimate the gas flow rate. That means you have to find the volumetric flow rate in meter cube per hour. Clear? Clear, beta? This is clear, everyone, please? Please? This is clear? Now, if it is clear, then we have to solve this problem. How? Please see. Now, first, what is that, beta? There is a carbon dioxide. So, some value it is given. What is the value it is given? R of carbon dioxide it is given. Gas constant of carbon dioxide, how much it is given? 189 it is given, and already it is given joule per kg Kelvin. The gas constant of carbon dioxide it is given. It is given in the question. Now, but here thank you. Now, thank you. The flowing fluid, now beta, this is your ideal gas. So, this is your ideal gas. Now, the flowing fluid is your ideal gas. Once you have the flowing fluid is your ideal gas, no, but you don't have a density. Why? Because, see, this is your Pitot tube. It is not a manometer. Mind it, beta. This is your Pitot tube. So, my dear, if you find the flow rate, so first you have to find, very first you have to, you know this is what, beta? Oil. This is your oil, and you know the specific gravity, that means density of oil. But you don't know the density of the carbon dioxide. So, carbon dioxide acted an ideal gas, you know that P is equal to rho R into T, equation of the state. If you know, then you have to able to solve PV equal to MRT. Now, from here, you can easily find density of carbon dioxide. What is the density of carbon dioxide? Pressure, which is flowing, R into T. What is the pressure, beta? Pressure it is given 170 kilopascal. So, pressure it is your 117 kilopascal. So, 17 kilopascal. Pascal. This is in Pascal. R it is in Joule. 189, and temperature always kept in Kelvin. So, what is the temperature? 20 degree. So, this is your 273 plus 20 degree. How much it is? This is your 3.07 kg per meter cube. This is the density of carbon dioxide. Now, you know this thing. If so, now apply the manometric equation. What is that? What is that, beta? Let's suppose this is section 1 and this is section 2. Clear? So, what is that? H is equal to what? Delta P by delta rho into G. You know this thing? Now, what is it? H is here. H is your 8 centimeter, that means 0.08 meter. Delta P, you have a delta P, you have a delta P. No, there is no any delta P is there. So, from this one, you can easily find. So, delta P is equal to anything, let's suppose P2 minus density of oil higher. What is the density of oil? Density of oil is, if you multiply, that means this is your density. It is equal to, if you multiply. So, if this is a specific gravity, from a specific gravity, if you multiply the density of water, the density of the oil you have easily find. So, So this is your delta P, and delta P it is there. Let's suppose, so P1 it is given kilopascal. So P1 it is given kilopascal. How much it is given, beta? So delta P first find, then we have to substitute, no problem. So delta P and density, how much it is? So density of oil how much? 0.827 into density of water 10 to the power. So this is density of oil minus density of, you have density of carbon dioxide, so 3.07. So 3.07, this is density of carbon dioxide into G value is 9.81. Just put this one. If you calculate the delta P here, 645 Pascal. Okay. So this is what beta? Delta P, that means P2 pressure. So if you, and the P1 pressure it is given, so P1 pressure, so if you find P2 is equal to 645 minus of, yeah, higher minus lower. So here you have to find P2 minus P1 of this value 645 Pascal. So here P2 it is your, so P2 pressure at this, there is a pressure, here is a low pressure is there, yes or not? But if you add, see here velocity is more, so if the velocity is more, pressure is low. So here the pressure is low, here the pressure is high. So here the pressure is high and here the pressure is low. Why? Because velocity is high. So the manometric will deflect ever. So P2 is always less than this value. This value. This value. This is how much? 17000. 17000 Pascal. That means 17 lakh. 1,70,000 Pascal. And here it is less than that. So we have to subtract that value. So here better to write P1 minus P2. You can write P1 minus P2. Why? Because P1 is higher, P2 is lower. So P1 minus P2. So the P2 value, it is your P1. P1 is how much? 170.3730 minus 645. If you calculate, this value is 169,400 Pascal. This is your P2 pressure. Pressure at this point, P2. Once you have a P2 pressure, you can easily find. Now P2, okay. Now my dear, see, this is like that, okay. Here it is your P2 tube, it is installed like that, yes or not? Fluid is flowing, yes or not? It is like that. Now, so we have to find, this is of section 1 and this is section 2. So we have to find the flow. See my dear, now we have to understand the pressure P1 and P2. Now you have a pressure in P1 and P2, but we don't have a velocity V1 and V2. But area we have. So we have a pressure difference, but we don't have a velocity difference. So from the velocity difference, one relation is the continuity equation. Why? Because diameter it is given. So one equation is continuity equation. From that continuity equation, you can stabilize one equation of the velocity. And again, there is a one equation is energy equation, and from that energy equation, why? Because the pressure difference it is given. So from that pressure difference, you can stabilize another velocity relation, and you can solve V1 and V2. Once you have to solve the V1 and V2, you can easily find the discharge. What is the discharge? Area into velocity. That is the simple funda. Okay. So to find, see here, where find V2. First, let's suppose find V2. Why? Because beta, why we have to find V2? Why? Because this is a Pitot tube at this point. That means if you take this section, so at this point the velocity is 0 at the nose. Pitot tube at the entry to the Pitot tube, the velocity is 0. But at this point there is a velocity. So you have to find the velocity. But at this point the velocity, but flow velocity is there. Flow velocity is there. This is your V1. This is your V2. But at this point, if you apply the Bernoulli equation at the point, not a section, at this point A and at this point B, same at this point B. So if you apply the Bernoulli equation from this streamline, so A and B, so at this A point the velocity is 0, but the cross section at this cross section, let A point the velocity is 0. B point the velocity is 0. B point the velocity is same as the cross sectional velocity. Why? Because there is a uniform velocity. There is a uniform velocity. So cross sectionally the velocity is same throughout. So if you find the velocity equation V2, use Bernoulli equation. Bernoulli equation. Now, so 1 at section 1. That means assuming, why? Because this is a Pitot tube. P1 is your stagnation pressure. Stagnation pressure. So beta, Bernoulli equation is applied at a 2 point, not a section. So Shreya, you are right. So if you confuse, you go to the previous YouTube lecture, beta. I have already, we have explained all this thing. What is the piezometer? So see, simply, okay, Shreya, I will just discuss you. See, okay, after the finishing the problem, yes, I will little bit discuss. Okay, so assume P1, it is your stagnation pressure. Why? Because this is at a point, and at the stagnation pressure, what is that? You have to take the velocity V at this point. That means V1 is 0. This is the characteristic of the Pitot. Now, apply the Bernoulli equation at this point A and B. So this is your PA plus half rho velocity 0. At this point velocity is 0 is equal to PB plus half rho into V2 square. Okay? Yeah, VB square. No problem. B. From here, you can find VB is equal to root under 2 PA minus PB divided by rho. So from here, you can easily find 2, and you have a pressure difference 645. This is your delta P divided by density. Which density? Density of flow. This is density of carbon dioxide. That means fluid which is flowing. The fluid which is flowing, what is that? 3.07. So if you calculate, this is your 20.5 meter per second. This is clear? First, please tell me, this is clear up to this point? There is any confusion? Please tell me. This is the velocity at point 2. Now, once you have a velocity at point 2, you can easily apply the continuity equation. Q is equal to A2 into V2. A2 you have, why? Because diameter you have pi by 4 d2 square into V2 square, V2. So d2 you have, what is the d2 you have? So if you put this value, the answer it is your 0.058 meter cube per second. Now it is in hour, so multiply with the 60. This is your second. So multiply with 3600. second, 1 second. So convert it into hour. This is your 209 meter cube per hour. My dear, I request you, if you have any confusion in this question, I will very happy. Again, I will very happy. Again, we have to explain it. No problem. Why? Because this question is really creates a confusion in the exam. This question is very straightforward and this is a conceptual question. But while you in the examination, there may be high chance to mistake. Many students get mistake. Why? Because they don't know. While you have to read this question, they are just simply assume this is your manometer. No, this is your piezometer. Now, Shreya, you have to this is not beta, it is that challenging question series, so we are not able to discuss in detailed manner, but I will give some brief introduction ki explain Pitot tube, piezometer and simple tube, siphon tube. See, this all are already covered. This is already covered in the theory session. This is a pure numerical session. So if you confuse, sir, see, if there is a manometer, so only this portion is there. This is the manometer. But if insert in the flow and the mouth is your opposite to the flow, that is your piezometer. That is your, not a Pitot tube. And the characteristic of the Pitot tube, the velocity at this point is 0. It is not like that, sir, this velocity, no, velocity at this point. Now once you apply the Bernoulli's equation, the velocity at this point is 0, pressure you have, but the velocity at this point is there, so you can easily find the velocity. I will explain you. See, what is that first thing is required? First thing is required to apply the Bernoulli's equation between this point. I will just tell you. First, you have to apply the Bernoulli's equation. Now, first thing. Now, during the application of, see, this is the point. This is the point. Let's suppose 1, and this is the point. Let's suppose 2. Let's suppose this is point 2. So apply the Bernoulli's equation. Now, so energy, so these are the same level. So potential energy change neglect. So apply the Bernoulli's equation, that means pressure. So P1 plus half rho V1 square. Now P2 plus half rho V2 square. Clear? This thing is clear? Now, my dear, P1 we don't have a value. P1 we don't have a, oh, P1 it is there. Okay, no problem. What is V1 here? So from the Pitot tube property, at this point, the nose of the Pitot tube, the pressure is stagnation pressure. You can say that there is a maximum pressure is there at the nose of the Pitot tube. When if you assume that the nose, the pressure is maximum, so energy, that means in the form of kinetic energy, very, very, very minimum. That is called the stagnation pressure. So if you assume that point 1 is the stagnation point, so you can, by default, it is your stagnation point. That means at that point, the velocity is 0. So this term is neglected. Now, P2, how to find P2 value? So P2 you don't have, no problem. V2 you don't have, no problem. No problem. V2 you don't have, no problem. But you know the manometric equation? From this manometric equation, you just put this value, H value. H value you have, delta P, the difference in pressure, you don't have. Why? Because P1 is there, P2 is not there. Now, density difference into G. Once you have to find delta P, it is there. Now, if once you delta P, you can find P2. So, if you find P2, put value here and you can easily find V2. Once you have to find the V2, just apply the continuity equation. A2 into V2, that's it. That's it. Is there any problem? Shreya, is there any problem, beta? Is there any problem? Please tell me. Now, take the next problem then. Yes, this is a very good problem, I am telling you. What is that? See this one. Read this question. What is that? A thin equilateral triangle plate is immersed parallel to a 1 meter per second. Okay? A stream of air at standard conditions. Okay, that condition it is given. Estimate skin friction drag on the plate. Skin friction. Acha, piezometer and siphon. Okay, okay, no problem. Piezometer and siphon. Okay, sir. So first tell me, this is what? This is what? This is what? This is what, beta? This is a piezometric tube. We can measure the flow, and siphon, sorry, Pitot tube, correct. Shreya, this is a Pitot tube. This is a Pitot tube. So from the Pitot tube and piezometer it differ. Piezometer it differ. This is a Pitot tube. There is a piezometric tube, it is a only vertical tube. From the piezometer, you can measure the standard atmospheric pressure. Piezometric tube, there is a standard vertical tube is there, that is called piezometric tube. Siphon it is not. Siphon, from the siphon there is a large pipe, and from the siphon we can have to measure also the velocity at inlet or exit, anything. But the siphon we can use from the large height, at the large height. That means there is any reservoir is there, there is a mountain is there, and another side there is another reservoir is there. So to connect these two, there must be a siphon. From one reservoir to another reservoir, if you connect, there is a siphon. Like that. See. See, my dear. See. There is a one tank, there is another tank. So if you, this is filled by the fluid, and this is filled by the fluid. Now if you put these two one together from this pipe, so this is your siphon. This is your siphon, beta. This is not a, this is your siphon. And siphon we can measure against the, why? Because if the height will increase, if the height will increase, there the pressure is low, so there may be a chance of a vacuum, to create a vacuum. And the vacuum, there may be a chance that the pressure, it is below the vapor pressure of the corresponding fluid which is flowing inside the tube. So from here, the fluid may be vaporized. Principle, principle it is there. How does that means? What is the principle? You can ask, what is the principle? What is the principle? The principle is gravity. Siphon works due to the gravity. Without gravity effect, siphon doesn't work. So what is that, beta? You create a vacuum. Why? Because they see this reservoir are differ. This is high reservoir, this is low reservoir. So there must be a different height. If there is a height is same, no fluid is flowing. So there must be create a pressure difference, and due to that creation of a pressure difference, the gravity will be helpful to flow the fluid. So this is the gravity effect. Now the fluid is flowing, and there must be increase the height. There may be a pressure which is below that the atmospheric vapor pressure of the corresponding fluid. So there may be a negative pressure is there. And due to that negative pressure, there is a evaporation or bubbles formation is there. And we don't require the bubbles. So we have to adjust the height so that we don't have, that means we have to design the siphon such that there is any vapor, that means evaporation will take place at this height. So how does the siphon is work? Siphon works in this due to the two pressure difference. That means there is also atmospheric pressure. There is also atmospheric pressure, but why the fluid is flowing from this to this? There is a elevation. If there is a same elevation is there, if there is a same elevation is there, and if you put the siphon doesn't work. Siphon doesn't work. So there must be elevation. Along with that, there must be a gravity effect. Clear? This is the theoretical part, beta. These are all the covers in the theory. Okay, no problem. Today we will have discussed the numerical. Okay. So just read this question. So a thin equilateral plate, just try to use, try to solve this problem. I am telling you this problem is very, very important. A thin equilateral triangle plate is immersed parallel to a 1 meter per second stream of air at standard condition. Estimate the skin friction drag on the plate. So you have to find skin friction drag. Skin friction drag on this plate. So my dear, this is a type of equilateral triangle, that means all sides have a 2 meter. And this is your, let's suppose this is your triangle, like that. So fluid is flowing. So the drag, it is a front and back both. The drag force, it is front and back both. Why? Because this is a triangular in nature. Okay, and the property it is given, density of the air given, and this is a free stream velocity. This is a free stream. That means the fluid is approaching with a free stream. That means all the velocity are uniform. It is approaching at 1 meter per second. The length it is given, the equilateral triangle, the length it is given 2 meter. Kinematic viscosity of the air it is given. And this angle theta, 60 degree. Angle is 6. See, theta it is 30 degree. So theta you have to assume like that. This is theta. This is theta is 30 degree. Why? Because equilateral triangle, all the angle it is a 60 degree. So theta is 30 degree, that means half. It is like, it is the question is given. This data is not required, but in this question it is given. Why? Because this is an equilateral triangle, and you know that the angle of interior angle is 60 degree. You know this. How to find this drag? Please, anyone? Please, anyone? I am telling you, this is a very important question. Okay. Now start this one. I will start this question, no problem. Okay, my dear. See, first put the coordinate. So this is our x-axis. This is your y-axis. And this angle, it is your theta, and it is given. Okay. Now, that means we are analyzing upper part of the triangle. If you find total, you just multiply with upper and lower 2. And then we again multiply 2. Why? Because front and back. Clear? So, for that one, now my dear, what is the approach? See, the approach is that when the fluid is flowing over the plate, does the flow over the plate is laminar or turbulent? That means entire it is laminar, or entire it is turbulent, or somehow it is laminar than turbulent. First thing is that. Accordingly, the drag force, yani skin friction drag, you have to find it. So first, whenever you have to see in the question there is a drag, skin friction drag, first you identify should the flow is laminar or turbulent. Accordingly, you have to use the formula. Now, my dear, for that one, you must have a knowledge about the maximum length of the plate. Maximum length of this plate. So, and if you find the drag, the area continuously varying, yes or not? Let's suppose you have to take this strip here, elemental strip. So on this strip, if you are moving, let's suppose we have to find the drag on this strip. So if you find the drag on this strip, and if you move this strip up or down, the area of this strip will change, so that the drag force is also changed. So why? Because there is a non-uniform, there is a area variation. So if you find the drag force on the given particular elemental area, then you have to integrate, that is your total drag on this upper triangular part. So this is your elemental part, and let's suppose this element part, it is the distance, let's suppose this is your x. This distance is x, let's suppose this is your x. And this thickness of this element is y. Thickness of this element is y. So what is the area of this element? Area of this element is equal to, this is what, dy. X into dy. This is the area. What is this length? This L it is given. This length it is given. And this is equilateral, so that all are length it is given. Now, we have to find the equation of this line. Very important. We have to find the equation of this line. Very important. How to find the equation of this line? So this is a straight line. What is the equation of this straight line? Please tell me. Y, the slope is negative. Mx, y barabar mx plus c. So m tan theta into x, and what is c? What is c? This c, intercept. And this intercept is L by 2 into L by 2. Clear? So from here, what is the x value? Y minus L by 2 divided by minus of tan theta, that means L by 2 minus y by tan theta. This is x variation. This is the x, and this x will change. This x will change. Why? Because y value will change. Y value will change. Now, my dear, what is the maximum length? What is this maximum value? See, at y is equal to 0, see, if we increase the y, x value is decreasing or increasing? If we increase the y, the x value is decreasing. So, where we have to find the maximum value of x? When y is equal to 0. If we put y is equal to 0, the x is a maximum value. So, if you put this y 0, this x is maximum. So, x max is how much? L you have to put 1 or 2 divided by 2. That means 1 divided by 10. Theta is equal to 30 degree. This theta is equal to 30 degree. If you put the value of x max, it is your 1.73 meter. This is your maximum length of this plate. Clear? 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 Now, if you find this maximum length of the plate, we have to find the critical distance. So from that one, we have to apply the Reynolds number. Critical Reynolds number is equal to free stream into critical distance divided by kinematic viscosity. You know this thing, Reynolds number? And what is the critical Reynolds number? Flow over the flat plate, 5 cross 10 to the power 3. U value it is given 1 meter per second, XCR, and kinematic viscosity it is given 1.5 cross 10 to the power minus 5 is equal to 5 cross 10 to the power 3. So from here you can easily find the critical distance. What is that? 7.5. Now my dear, just tell me. Now please, 9th standard, 9th student. Yes beta, please tell me. PMS Patil, 9th student. Yes beta, please tell me. There is nothing for you in this platform. There is nothing for you for this platform, but this is not a 9th standard. Okay? Find another platform. Okay? Now, so this is a XCR, and XCR it is equal to 7.5 mm meter. This is meter. Now please tell me the flow is laminar and turbulent. Please tell me. 7.5. Yes. Please tell me the flow is laminar or turbulent. Please tell me, beta. Everyone, please. The flow is laminar or turbulent? Please tell me. Please tell me the flow is laminar or turbulent? Compare these two data and just tell me the flow is laminar or turbulent. Everyone, please. The flow is laminar or turbulent? Please tell me. The flow is laminar or turbulent? What is the critical? The critical distance, the critical length of the plate is the plate up to which the flow is laminar. Above the critical length, the flow is turbulent. No, so my dear, what is the critical length of here? 7.5. And what is the maximum length of the plate? 1.73. So maximum length is, yes, very good. Maximum length is below that the critical length. So the flow is laminar. Clear? So this is greater than X max. That means 1.73. That means laminar boundary layer. Laminar boundary layer over entire plate. Entire. This is your first job. This is your first job. Entire plate. Now my dear, once you have to find the flow is a laminar, then we have to apply the drag force. And my dear, this drag force will change. So we have to find this drag force we have to find on this elemental. So there is a small drag and then we have to integrate it. So the drag is, that means we have to find, now on this element we have to find, this is your x and this is delta y, dy. So we have to find the drag on this element. Drag on this element. So what is the drag? Let's suppose d of d, small drag. What is that with a drag? CD, drag coefficient, and this you have to take a drag coefficient for the laminar, not turbulent. So CDL into dynamic pressure into dynamic pressure. What is the dynamic pressure? Half rho U infinite. Clear? This is clear? Now, So this is a not a pressure. So dynamic pressure and this is a force now. So this pressure and required force. So must be apply the area. And what is the area? X into dy. Don't forget. Why? Because this is a force. So force is equal to pressure when we multiply the pressure into area. Okay, no problem at all. Now, this L is for laminar. Now, my dear, please listen carefully here. Now, you don't have this drag coefficient value, yes or not? Yes or not? You have? No. In the question, it is not given. So, how to solve? Better, my dear, in the gate, it must be given for the laminar according to the Blasius equation. That means for the gate, this value it is given in the question. Okay? What is that? 1.328 divided by Reynolds number local half. This is for the gate, it is given. No problem. Don't remember. It is given. And this is for the laminar. You don't remember this value. If you remember, it is helpful for the IIS conventional. In the conventional, it is not given sometime. So you just remember it from the laminar drag coefficient is this value for the external flow. So this is for the external flow. Yes or not? External flow. This is according to the solution of Blasius equation. Okay, now into half rho u infinite square into x dy. Clear? Now, what is Rex? You know that local Reynolds number Rex is equal to u free stream into x divided by kinematic viscosity. You know this thing? Put this value here. Put this value here and rearrange it. Put this value Reynolds number here and rearrange it after this. See, my dear, this step is very, very conscious at this step. Otherwise, 90% chance you have to mistake here. Put this value here according to this Reynolds number. Rearrange all the things. After rearranging, it is look like that. Small drag, it is your 0.664. Just do the practice at home. Square root of kinematic viscosity, density u infinite 3 by 2 x पे power 1 by 2 into dy. Just do the practice. Okay, beta. Why? Because there may be high chance to mistake here. So once you have to this value of drag, now you have to integrate it. Now you have to integrate it. So after put this value Rex in this one. Rearrange this value. So if you rearrange, this is look like that. Clear? Just do the practice. Just do the practice. Okay. Now we have to integrate it. Total. We have to find drag force on this element. Now you have to integrate it. Now, my dear, during the integration, be careful. We have to find a total drag. So if you find the total drag d, you have to integrate it. D of d. Now, what is the integration limit? You take this as a coordinate. So x, so it is here 0 to L by 2. The integration, it is your y equal to 0 to y equal to L by 2. Yes or not? Y equal to 0 to y equal to L by 2. Now, my dear, y equal to 0 to y equal to 0. There is a very important, I am telling you. Y equal to 0 to y equal to L by 2. This is the first. This is your only upper part of the front triangle. This is the value is only upper part of the front triangle. But there is a how many parts? 1 and 2 parts. So this multiply with the 2 here. So this 2, if you multiply, that is the total drag on only front part. But there must be a back, so multiply also 2 here. Clear? Don't forget about 4 value. 2 is for top and bottom. 2 is for top and bottom. And this 2 is for front and back. Clear? This 2 is for top and bottom. This 2 is from front and back. Clear? Clear? So here is 4. So just do the integration. Now, my dear, see this. Okay, just do the integration. So d is equal to integration of L is equal to y is equal to 0 to y is equal to L by 2. Here 2 into 2 into 0.644 square root of, this is your kinematic viscosity, density u पे power 3 by 2 x पे power 1 by 2 into dy. Okay. Now my dear, this integration is with respect to x, with respect to, sorry, this differentiation, this integration with respect to y. So please convert this x into the y. So instead of x, what you have to put? X is equal to y, x is equal to L by 2 y minus y by tan theta. Already you know that x is equal to L by 2 minus y divided by tan theta. Just put this value here. Just put this value here. L by 2 minus y divided by tan theta. Put this value here. This 2 is for upper and lower. This 2 is for front and back. Clear? Now put this value and rearrange it. So this is your d, and d is equal to 0.626 rho u L पे power 3 by 2 square root nu divided by tan theta. This is the after rearranging. After you have to integrate it, this value is there. Now theta is constant. Theta is constant. Now density you have. See, density you have, u you have, L you have. Put all this value. Kinematic viscosity you have, theta you have. Put all this value. The total drag, it is your 1.1 cross 10 to the power minus 2. That's it. Clear? This is your question. Clear, beta? So this is your drag force on the triangle, this triangle. Clear? Everyone? Solution is clear, beta? This is clear, everyone? Please tell me. This is clear? This is clear, everyone, please. Okay? Put all this value. So what is the approach here, beta? The approach, it is just you have to find the flow is laminar or turbulent. For that one, once you have to find the laminar or turbulent, we have to successfully seen that sir, the flow is entire plate is a laminar. Why? Because the critical length is higher than the given length of the plate. So given length, this length is the plate 1.73. Now, once you have to find the laminar, just you know that the drag, this drag is for the small elemental. So you have a CD drag coefficient for the laminar L 1 by 2 rho u infinite into area. What is the area? x into dx. You maybe also integrate vertically, no problem. Okay, vertically you maybe also integrate, no problem. Now, for the gate, it is given value. See, in the gate, the drag coefficient for laminar and the drag coefficient for turbulent both are given. So it is not like that case, sir, once you have a drag coefficient for the laminar, so we can assume only the laminar formula it is given, so we can apply. No. In the gate, the drag coefficient for the laminar, that means coefficient of drag for the laminar and coefficient of drag for the turbulent both are given. So you have which formula you have to pick, just we have to calculate this one, this is the flow is laminar or turbulent. Once you have to understand that, sir, the flow is laminar, just put this value over it. Now then you have to rearrange it. This during the rearrange it, be careful. Be careful. After rearranging, just to take on which portion in the question, they are asking. Which portion? So they are asking the total drag, and the plate geometry, it is for front and back both. So this is your from front and back multiply with the 2. And we have to take the area which is only upper part of the triangle. So there are two parts, upper part and lower part. So multiply with the 2. Now here it is there is a integration with respect to y. So convert x into the y. Put this value all. Find the answer. Clear? Clear? Now we have to take the next problem. Yes. This is your next problem. This is very important again. Please read this question. These all questions are 2 marks. Please read this question, beta. This question is exclusively for the civil. Also there is a mechanical, but more chance it is in civil. Okay, civil department. What is that? A gravity settling tank, okay, are sometime used to separate the particle from a fluid stream. Okay, estimate the critical length L for the capturing a particle by the gravity settling in the channel shown below. Express your answer in terms of channel height, fluid velocity, the fluid density, the fluid dynamic viscosity, particle density, particle diameter, and the acceleration due to gravity g. You may assume that the particle diameter is small, very small. That line is very important. You may assume that. Why this assumption it is given? That is the very important thing. You may assume that the particle diameter is small, very small, and the fluid velocity profile in the channel is uniform. All the point, that means uniform fluid flow. That means a fully developed. Uniform, no, it is not like a uniform. That means there is no any, that means all the flow, this uniform, that means all the cross section, the velocity is the same, all the cross section. It is not that, sir, at this point the velocity, this point velocity is changing. No, over the cross section, at each and every cross section, the fluid is same, that is velocity is same, that is called uniform flow. Okay. How will the length L change if the particle diameter is doubled? That means they are asking also, if the particle diameter is double, what is the length? Clear? Clear? Just to take a snapshot of this question and start with the solution. Why? Because this question is very important question. Okay. Right. So see this, my dear. This is gravity settling tank. So what is the gravity settling tank? That means you have to assume like that, beta, ki before exit the particle is captured. That means it will settle down before exit. That means you have to supply the particle, that means the particle segregation takes place. That means more density will fall first, then less density, then less density, then less density, and it will be separated by the different density of the particle. It is like that. So in order to capture the particle, that means if you find the capture, that means it is inside the channel, it is not, you go beyond the channel. So if you capture the particle inside the channel, we want that the particle to settle on the base before passing through the device. That means when it will be settled, that means you want that the settling, this time, that means settling time, and this is transient time. This is settling time and this is transient time. So settling time is must be less than the transient time, so that the particle is settled in the settling, in this particle settling, okay, in this gravity settling tank. So that means this is your particle, okay, this is your particle, okay, this particle is try to move in this direction. So in this direction, this is your settling velocity, the terminal velocity. So you must be have that is time of settling, time of settling is less than time of transit. Yes or not? So that the all the particle will capture time of settling. This was settling. Time of settling is less than the time of transit, so that all the particle will settle down. Okay. So in this direction there is a settling, and in this direction there is a transit. Okay, no problem. Now, what is your time of transit? How to find time of transit? How to find time of transit? This length divided by this velocity. In this direction there is a velocity, u. Yes or no? U. So this is a time of transit. Okay. Now what is the time of settling? What is the time of settling, beta? Time of settling, this is the height h divided by, in this direction what is the velocity? There is a fluid, na? What is the velocity? There is a velocity, is terminal velocity. That means the fluid particle is full of the fluid. There is a fluid. So this is particle suspended. So this suspended particle will try to fall down. So the particle which is fall down have attains its a terminal velocity just after from top to bottom. It is not like that. Yes, it is sometime in the mind, the student community in the mind there is a confusion. Ki sir, terminal velocity, it is a velocity after the particle attaining the uniform velocity. That means a uniform velocity downward, and it will take some distance. It is not like initially. But in this case, we have to assume that the particle will attain its a terminal velocity from the top to bottom. It is not like that in between. Okay. So u of terminal, u of terminal velocity. Clear? Now, my dear. L you have, U you have, H you have, but U terminal you don't have. This value you don't have. And this terminal velocity, if you find for that one, equilibrium, particle equilibrium. So, this is your particle, okay. This is your particle. On this particle, in downward, there is a weight, and in upward, there is a drag, and also there is a buoyancy. So in this one, there is a buoyant force and there is a drag force. Clear? At equilibrium. So net force, that means upward positive. That means you have to take drag force plus buoyant force minus weight is equal to 0. Clear? What is the drag force, what is the buoyant force, and what is the weight? You have to just put this value. Now, so for that one, weight of the particle. What is the weight of the particle, beta? Weight of the particle is what? What is the weight of the particle? Density into volume. Density into volume is the mass multiplied with the g. Why? Because in this direction. So, mass of the particle, g of the particle, this is the weight. This is the weight, and what is the mass? Density of the particle, volume of the particle into g. Yes or not? Yes or not? So density of the particle, it is given. What is the mass of volume of the particle? Pi by 6 d cube. Density of this particle. So this is your density into g. So this is your weight of the particle. This is the weight of this particle. Now, what is the buoyant force of this particle? Fb, buoyancy force. Density of the fluid, which is immersed, that means density of the fluid into g, and this is volume of the particle. Why? Because this is generally a displaced volume. This is fluid displaced. Fluid displaced. And this fluid displaced, but the particle is fully immersed. Fully immersed. That means the volume of fluid displaced is equal to volume of the particle. Why? Because it is fully immersed. So, density of the fluid you have, G you have, and volume of the particle is pi by 6 dq. So, this is your buoyant force. Clear? This is your buoyant force, and this is your weight. Now, what is your drag force? That is very important. Drag force. What is the drag force? Fd. Drag force is equal to drag coefficient half rho, and this is vertical direction. So you have to u of terminal square into area. Area is what, beta? See, this is a particle, okay, and this particle is going to downward. So this projected area, this area is your, over that there is a drag force will act. So this is your projected area. This is your diameter d. This is your motion. This is your diameter d. So this area is your projected area, and this is your cross section, pi by 4 d square. Clear? Pi by 4 d square. So this is your projected area, pi by, very important, pi by 4 d square. Clear? Now, that is okay. Now, my dear, How to find CD? Drag coefficient. See, the particle is very small. The particle is very small, so the Stokes flow regimes valid. Stokes flow. And for the Stokes flow, that means for a small particle, this is very notable point I am telling you. Very small particle, so if there is a very small particles, that means Stokes flow resumes. Stokes flow. And for the Stokes flow, what is the Reynolds number over base on diameter D? Is equal to 24 by CD. CD is equal to 24 by Reynolds number based on diameter D. 24. And what is RD? RE, Reynolds number of D, is equal to U of terminal into diameter divided by kinematic viscosity. Put this value here, CD. This is a very important observation I am telling you. Put this value CD here, rearrange it. So, the drag force is if D, put all this value here back. What is that? CD 24 by RE, 24 by Reynolds number based on diameter, into half rho U terminal square, half density of the particle U. So in this one, there is a fluid is there, density of particle. Okay. And U terminal square. What is the area? Pi by 4 d square. Clear? Clear? Now, what is this Reynolds number? 24, and Reynolds number is what? U terminal into D. That means if you find rho, U terminal into D divided by dynamic viscosity, it is there. Clear now? Clear? So this is there into half rho U terminal square into pi by 4 d square. Rearrange this all. That means there is something you cancel. This 4, that means this 4, this 2, and this is your 3. Clear? Density, this is your density of the fluid, obviously. Fluid, this is your fluid. So this density cancel out. This terminal velocity, there is a one terminal velocity, it is cancel out. This D and this D is cancel out. Clear? 4 is cancel. So if you rearrange this is your 3 pi mu U terminal into D. This is your drag force. And this is also called Stokes law. You can remember this value, no problem. So these are the proof. Now put all this value here. Put all this value here, beta. That means first density of the particle pi by 6 dq into g minus density of the fluid pi by 6 dq into g minus 3 pi mu u terminal into d, and this is a 0. Yes or not? This is 0. Now, if we rearrange this, the terminal velocity is equal to density of the particle minus density of the fluid g d square divided by 18 mu of the fluid. This is your terminal. Now put this value here back. This is terminal velocity. Put the value back here in this one, u of terminal, and take that and find that aspect ratio. That means T of settling is less than T of transit. Rearrange this one, H divided by U of terminal, density of the particle, density of the fluid, G d square divided by 18 mu f is less than L by U. Okay, U is the transit. So L by H, design L is the length of the channel, H is the gap, is greater than 18 mu f U divided by d square G density of particle minus density of the fluid. So if L by D is greater than this value, there must be a capture before it will transit. There must be a capture before it will transit. That means if you designed L by D in this one, that means this is your channel. Let's suppose this is your L and this is your H. So if this is your particle, and if you design, all particles are settled before it will exit. That means heavy particle, that means this particle will like that. So if you design L by H is greater than this value K, all the particle will capture. Clear? All the particle will capture. So I hope now we have end up at this point. And now, my dear, really this question is very, very, very important question, I am telling you. So just go through the question before entering to the examination, at least this question. How to find a drag, terminal, weight, all these things. Clear? And also do the practice of according to your calculation. Okay, my dear? So up to that, thank you. And my dear, tomorrow we will discuss the most challenging question of the subject of thermodynamics. So we have to cover that subject of a thermodynamics, and let's see how many questions we have to cover it. And also the question is very, very good question. Okay, up to that, thank you, bye bye, take care.